So today I'm going to talk about a distributed framework for producer and consumer that guarantees message delivery. Conceptually, here producer is just something that is capable of generate events or is a sender that sends a message. And consumer is just something that's a target of the message or it's a receiver of your message. So it's really, conceptually, it's just a sender and could be the receiver. And at TechTest, we have been using such framework heavily, and we found it's really useful in terms of boost your productivity and reduce the new service rollout time. So if you have any applications that can be abstracted or modeled using producer-consumer diagram, you may find this system really works for you. Here's the layout of my presentation. So first of all, I'll walk you through the problem or issues we are trying to tackle with. Then we'll dive into the detail of how we implement such a system that guarantees the message delivery. Then we'll talk about details of each components. Then by the end, I will give you a demo of an application I thought of that is using such system. So give you an idea how I set up the system and start to use it. Here's a very classic producer-consumer diagram. From here you can see that we have a consumer and the producer. They normally reside in the same host or server. So they communicate via some shared status, such as they can do shared memory or some pipe, right? And also can control via some mutex. So the capable can somehow control them each other and to consume a message that's generated from a producer. And this all can be done locally, so reliability is really not a big concern here. The relationship can be kind of abstract, like it's a FIFO queue, like first in, first out queue between them. So producer is simply put something in the queue and the consumer pick it up. So, but such a diagram is, since they are kind of scoped by the location, basically the inside some same host or server, so this usage is really very limited. And for us, is really, we want something it's distributed. We want that user, the producer, and the consumer can be anywhere in the network, right? So, but such a freedom of the location comes with great cost. Imagine that your consumer link might be broken. So what happened to the message then, right? So someone had to take care of that. Even the network is very good, but what if we introduce a bug somehow in the new code and roll out? Well, processing event, it crashed. Man, where's the message? How can I get that back again after I fix the bug, right? And it's also possible that if during your processing logic, you need somehow, let's say, send a message to your downstream server, right, or do a HTTP post. What if that bounce back with 400 or 500 error? So here you can see that reliability, or how do we guarantee this message delivery, is really a big challenge here. And the solution actually is really simple. What if we just send some feedback to the producer, say, hey, can you resend me the message XYZ, right? It sounds really simple. But it's really easy to see, really hard to implement. Imagine in such a case that we have a very big fat pipe between producer and the consumer. So even before the producer receives the acknowledgement or feedback somehow from the consumer, right, it may already send 100 or 1,000 messages already. So imagine you have to somehow buffer or store such kind of message for future, potentially, probably only 1% or 0.1% of retransmission, right? But that's a huge burden on your design or your producer. About this, think about if you needed to implement or develop 10 different kinds of producers. You don't want to waste your time, say, duplicate the very similar retransformation logic into all your producers. That's a great waste of your talent on time. So ideally, we want to design the network. We want the network handle it. So the network should be something that's smart enough. It can deal with this kind of retransformation or guarantee the message delivery. So it frees our developers up to focus on the application logic. So this is really the goal of this talk. We want to make sure the network handles the message delivery and guarantee the retransformation. Even if my consumer somehow crashed, I want the message to send me back sometime later. So this is the goal. So while designing our system, we basically following some guidelines. So we wanted the producer and the consumer be simple enough, but not simpler. And certainly, there should be no location limitations that the consumer and producer can be anywhere. They can be at the same host or another different host. So it shouldn't really matter. And there should be no limitations on the number of the same producer or number of same consumers. So you can have 1 producer or 10 consumers. It shouldn't matter. And the system should be self-provisioning. This means if tomorrow you come up another idea, hey, I want to put another kind of consumer services into this system, it should just work. You don't need to ask anybody, say, oh, I want to provision something, can you do that tomorrow? Right? So our idea is we design a certain addressing schema that your new producer and consumer will just work as long as you follow that kind of rule. And certainly, the last one is we want to use some off-the-shelf technologies. We don't want to redo this whole thing, start from scratch. So here is a very high-level overview of the system we built. So from the graph, you can see we have 3 queues, mainly 3 queues. The first queue is the message queue. That is operated by the producer and the consumer mainly. So producer is simply do enqueue to the message queue, and receiver do a dequeue. Here I call it a very special dequeue because we actually had some change on that. And the second queue is the retry queue. So anything that consumer pulls out from the message queue, it will put into the retry queue for future redelivery in case somehow consumer does not complete that message successfully. So then you get a chance to retry it. So we have a retry scheduler that actually consumes anything in the retry queue and figure out a future time that should be retried. So for each event, you can attach some timeout value. See, at 10 seconds later, I want this event to be expired, and you put into the expired event queue that our retry distributor can look it up, say, oh, this is expired event for message queue 1 or 2, that should be redelivered to the consumer. So we use 3 queues and 2 big components. One is the retry scheduler and retry distributor that guarantees your message will somehow magically reappear in the message queue for the consumer. So I will use the flow, walk us through, think about that way. Think about the producer generate event A, and it simply puts in the queue. So then consumer will pick it up, use this SDQ technology, and it will at the same time, that is atomic operation. So you pull something out of the queue, you put into another queue immediately. So one operation, you do two things. Then the retry scheduler will pick it up, say, oh, OK, I'll schedule this for retry in 10 seconds later. So think everything is fine, that consumer processes successfully. So it will send the feedback back to the system, say, hey, I'm done, so just cancel this event and remove it out of the system. So then the retry scheduler will be happily to cancel the timer, so everything gone. So imagine somehow consumer died or failed to send the feedback back. So then that timer will clicking and fired in 10 seconds. Then the event will put into the expired event queue. Right, then the retry distributor will look at the event, see, oh, this is for message queue here. So it will put into this message queue again. Then consumer got a second chance to pick it up. So that's the way it works. So to facilitate the programming of this producer and the consumer, we actually abstracted all this operation into a Java script library and Erlang library. So from producer and the consumer point of view, they are simply do DQ and enqueue. For consumer, the extra step is send some feedback. So this kind of framework or infrastructure or technology we used is totally transparent to them. So this gives us actually a flexibility. So you can simply remove the whole backend, just keep the interface as the same. You don't need to touch the application at all. Right? This whole thing will still work. That's how the layered structure works very well here. And we built this whole system is actually using this redis technology. Redis is an open source NoSQL library. So all this message queue, actually we map to the redis queue structure. Right? The retry and the retry scheduler and the retry distributor, actually we use some Node.js code that this does the magic. But this whole thing is actually resides on the same server. So we have a Redis server running. That's a regular Redis. Then we have one node component actually kind of acting as a retry thing. So they work together, become this system. So the question is why you want to use Redis, right? So one thing we feel is Redis is something it's really stable, and it's running really, really fast. It handles thousands of requests per second without any complaint. And most importantly, I think, why is it supports this atomic operation. Imagine in the graph here, right? We do special DQ. We do DQ and put the message into another queue immediately. So this has to be done as an atomic operation. Imagine you do it in 2 steps, right? So you do DQ, then you do another enqueue to the retry queue. But your second operation might fail, right? Then you miss the chance for retry. So this has to be atomic. And Redis is the technology actually we have been using a lot, so we kind of have high confidence. If a system we build around it, and it should just work. So this is basically why we choose Redis. The next thing I want to talk about is how do we achieve this self-provisioning. So no configuration change, and no system has to touch the server to restart to load the config or thing, right? Whenever you have a new service, you follow the convention of the addressing, it will just work. So for each event, whenever the producer put into the queue, we actually ask them, see, you have to give me a service name. So this service name is a random point that producer will put into the queue, and the consumer will know I need to consume from that. So it kind of become a bridge for consumer and the producer, right? And the service name is also used by the retry distributor because it's simple to handle one queue, right? It needs the retry distributor to look at the service name and figure out, and this expired event is for whole, right? So this is another use why we need this service name. So the second item is the timer ID or the event ID. From the consumer point of view, it's getting some event, right? From his view, it's an event ID. So when he sends the feedback back to the system, it's using this event ID, say, hey, I'm completed or failed. So the timer ID is actually used by the retry scheduler. Because from retry scheduler point of view, everything is a timer. So when he needed to cancel such event, he's using this timer event to cancel these timers. So this kind of two concepts, but it's the same thing. Timer ID and event ID in the system, actually the same. So here, example, we use basically each event, we have a prefix as a service, right? Then you specify your service name, then colon, then the timer. Last portion is some just UUID to identify your timer. So using such addressing schema, basically we allows any new services can be added easily into this system, but you don't have to provisioning or ask anyone to touch your network. So next, I will walk you through each of the components, see what kind of operation they do, so you can start familiar with the system and get deep idea of how the thing works. So first, I will talk about the producer. The producer behavior is really, really simple. So using the library we give you, so you simply do queue client in queue. So this triggers the event sent to the message queue immediately. And if the consumer is there, it can pick it up and consume it. Another option is you can actually deliver that event in the future. Let's say you want to create a time. Let's say I want to deliver this event 10 seconds later. So in this case, actually, the retry scheduler will get it, and it create a timer for it. Then after 10 seconds, it will put into the queue for the consumer. So basically, the producer can do send event immediately, or you can actually schedule some future events. That's the way you can do with the system. You do two operations. You either send immediately, or I can schedule something, or tomorrow I want to do something. So that's the beauty. Next, I will talk about the consumer. So here, consumer is doing a special DQ. It's using the redis BR pop L push. B means something blocking. So if the queue is empty, there's no event. So the consumer will simply block and wait for the event. This is useful because you don't want to do the busy check. That's wasting a lot of energy. So if there's any event in the queue, it will simply pop it up and push to another queue by the end. Right? So this is one operation. So you get the event from the queue and push this event to another queue in one atomic operation. So it's a very special DQ. Once it gets an event, since it's the distributed system, so it had to check if the event is somehow consumed by myself already. Right? If it's yes, then it simply tells the system, oh, I already completed, so just cancel any future retry, right? Remove it. So otherwise, you then start your processing logic. That's your consumer logic. So do whatever you want. Once you finish it, you always call complete to the system, acknowledge that you have done. Otherwise, you will get retry again in the future. You don't want to process this event successfully 10 times. So to facilitate the operation of the consumer, we actually define a join queue consumer behavior. So it simply gives you two callback functions. You implement init function, then handle event function. So init function basically it allows you to set up certain state that you might need in your event handling. And in the handle event call, you will get a tuple that is the ID of the event you are going to use to tell the system, I'm complete, so please remove for retry. And the payload basically is some opaque data that producer sends you, so you know the structure of that. So you have to agree somehow, you know, to pass it carefully. And this is the main two functions that a consumer needs to implement. So all the redis connection and this thing are kind of handled in the queue consumer already. So from consumer point of view, here's a simple example, right? I basically have a test service consumer, and it implements the behavior of the join queue consumer. And it provides two functions. One is init, another is the handle event call. So init here, I simply put 0 as my initial state since there's really no need. And in the handle event call, I simply log the line, see, I received the event. Then we will call the queue client, see, complete. This is the service name, and this is the ID. So this is the whole logic at the consumer side. So you simply implement two functions. Then all the heavy lifting, DQ, or check this status is handled or not, it's all handled behind the scene. The retry scheduler. So retry scheduler actually is a very important thing in this system because it has to schedule all these events for future retry and maintain the meaning of timers. So for retry scheduler, it simply work on this retry queue. So it simply do a DQ. And certainly it's a blocking call as well. The BR pop. So it's blocking call if there's no event. Otherwise, it was simply in a loop. So it also does a check, see if this event actually being handled by the consumer or not, right? Because consumer and the retry scheduler, they are two kind of totally independent process, right? They might race to each other. Imagine one case is consumer is really, really fast. So any event put in the queue, it will consume immediately and the call complete. But the retry scheduler might just start to get from the queue, right? So you don't want to schedule this event again. So that's the reason it has to check this event has been handled or not. If it's handled already, it simply ignore it. Otherwise, it will also check. I don't want to waste the system for retry if something is really, really bad, right? So we put some maximum number of retries. So if something really goes bad, then you retry certain times, this event will flood out your system. You don't want to have one event, it's looping forever. So if it's not exceeding the retry maximum number of retry, then it will schedule a timer for it. The timer actually we implement use the redis, the sorted set. So using this sorted set, so the timer operation is it's inside the timer delete. This timer is really log an operation. So next is the retry distributor. So retry distributor is really a very simple kind of operation here. It's simply DQ any expand event, then put this message into the service name that in this event to the right consumer queue. So the reason is why do we need this one, right? In theory, this retry scheduler can put this message queue directly, right? It's really no need you add a second component as the retry distributor. But we feel like this kind of more kind of cleaner. So retry distributor actually somehow you can implement another kind of distribution logic if you need. Although initially we think, oh, but it's really simple based on the service name. So if you need to do some complicated distribution logic here, then adding a retry distributor, it makes a lot of sense. But we haven't kind of find such usage in our system yet. It just started designing that way. So we feel there could be something expand here. That's the reason we separate out. So we have been using such system for quite long. It's more than 1 year already. And the thing, so what works well for us is we feel it really works well is the self-provisioning thing. So whenever we have a new service, it just works well. So using this addressing schema well, and you don't need to worry about any provisioning thing or config thing. So that's really something works very well. And second thing is the system doesn't degrade. Let's say if you have a service is really, really slow, a slow consumer, or this consumer has been stopped for 2 days, and you find out there's tons of millions of messages into the queue pending for the consumer to pick it up. So the system doesn't degrade even you have millions of messages in that queue. It really doesn't matter. The only matter is it consumes more memory. So somehow you need to alert the system, say, oh, you have to fix this consumer, otherwise I'm going to delete all your messages, right? Because it eats up all the memories. Another thing we found out is the system is reliable, and it happily handles millions of events each day, so it's a good one, production quality. So what kind of lesson we have learned? One thing we found out is the Redis remove is really, really expensive. Why we find out is we have in our early release, right? We have actually, the system doesn't scale if you have a consumer stop for 3 days. We found out, oh, there's actually millions of messages in the consumer queue. And our first release is we're trying to do remove whenever the consumer tells us, oh, I consume one event. So we do remove from this message queue. That's ON operation. So then our system, it become like snail. So we were debugging, hey man, what's wrong with our system? It just doesn't work. Each operation, it takes seconds because remove is occupying all your CPU. And later we found out, oh, because the one consumer degrades and it's calling this complete, we do the remove. So then we kind of reshuffle our system, so forbidden use the remove, so no more remove. Another thing we learned is that Redis expire is a good one, right? You can set expire with a certain time stamp, then this key will be gone. So initially we think, oh, this is a really good one. We can use this as a timer. So our early release of this system is we're using Redis expire to set as a timer. So it works really well. So when we have only a very small system, have hundreds of keys, expired keys, right? But later on, when our system grows, we have like millions of events to handle and the tons of timers there. Then we found out, man, it's really very strange. Sometimes this event you schedule 10 seconds later, it just comes out like 2 hours later. What happened? So then we dig into the Redis code and read this posting a little bit. Oh, we found out, man, the Redis is using the randomly kind of schema to pick certain random keys to check if they are expired or not. Then if they're expired, then they will delete them, right? Since it's random in nature, then there's some unlucky guys will never got picked up. So then we ditch this expired schema, so we start to use the Redis sorted set and implement checking on that portion. So that's the way we do the timer. So next, I will go through the setup of the system and give an example of application that use this system. So just to walk through how the flow looks like. So I come up with a weather station kind of application, right? We have a producer that basically it's a weatherman. He used some very rudimentary tool. So he has some pad that called Guanhua. That is capable of telling if spring is here by the shadow, but it's also capable of telling the weather if it's only 2 stages of weather. So it's sunny or not, or rain or cloudy. So this is really interesting pad that can tell the weather. And the consumer basically it's a join server code that consumes this report and post it to another weather station. That's a simple web server I set it up. So the website is simply hosting the only current weather report. And since this is a report from Guanhua, so people really have high interest on that. So we got a big screen in Times Square to show the results. But the weatherman really he got is very reliable delivery system he got. So first I wanted to do is we'll set up the.
Can you make the font bigger?
Okay. Does it view better?
You guys see that? Yes.
So we will, first thing is we need to start the redis. So I'll start the redis first. So first thing is to start this redis. Then second thing is to start this retry scheduler or the retry distributor. Those are the node code. So we will start the node timer. I call it node timer. So we got these two components started. Then we will start the website we have. This is a simple website I implemented to use the Node.js. We will need the browser here. So the browser simply load its initial state, the default state, sunny state, right? And so next I will start the producer. So this is basically I got a terminal for Erlang producer that can be posting something. Then we will start the same thing because it's another, we can start the consumer here. Basically I will call join queue consumer start link. So this join server start call basically tells this is my service name, that's a word service name. And this word consumer basically is the module for callback calls. So you start this consumer. So next thing we will use the producer. We will simply do an enqueue here. The typo? Yes, thank you. So we will report doing tomorrow. Then we go back to our browser and reflect it. So you guys want to guess how I do this updating real time at the browser? Anyone want to give a shot? So it's really a simple JavaScript trick. I ask this browser to reload every 2 seconds. So then we will report cloudy next. So it got cloudy. So, and another thing I want to show is we actually can schedule a report later. So we will use a timer. So we will create this timer. Let's see. I don't want you guys to wait too long. So we will do 10-second timer. But we need to change this stage weather a little bit. So we will go back to the sunny in 10 seconds. Actually, this call retains this timer ID in case you want to cancel immediately. Then about 10 seconds later, we should see something changed. So this is how you schedule the future event. So next, I'm going to do something failure case. So let's see how the system can recover it. So first thing is we want to bring down this consumer, see what happens. So we will do join queue consumer stop. So basically, we'll kill this process, so consumer is gone. Then we do another enqueue. We do enqueue ring. So nothing happened here. Then let's bring back this consumer. It posts successfully, so this event is there, so guaranteed to be there. The next thing let's try is to bring down the downstream web server. Let's see what happens. So basically, I will bring down this web server, and this guy complained actually that it couldn't load this web page. So then we go back to the producer again. Let's see, we want to report sunny state again. So from the consumer point of view, actually you can see it's complaining the post error because it couldn't connect to the web server. Then let's bring up this node server, and the event actually is going to be retried in probably 20 seconds or 40 seconds based on the number of retries. So it already retried 2 times. So we do the exponential backoff. I think sunny probably is not a good one because our initial state is sunny. So let's try something different. But it's got the weather report sunny, so let's try different. Let's stop this one and do rain state. So consumer complains post error. Then let's go back, bring up this website, and reload this one. It's coming back actually very fast. So from here, you can see that consumer says post is successful for this ring event. So even the downstream is down, but the system guarantees that this event will be there for you to give a second try or third try. So by default, we actually retry 5 times, and with the exponential backoff, so we don't want to loading this system for unsuccessful retry too fast. So here are some links we have. So the Redis link and Node.js is open source. The retry scheduler and the retry distributor is you can find under my GitHub repository, the node timer service. So here concludes my talks. Thank you.
Any questions?
Yeah.
On the flowchart that you have for the retry scheduler, where was it actually putting things into the expired event queue? Which I wasn't sure where that was happening.
The retry scheduler, right?
Yeah,
The next slide.
Where it says,
So,
where is it actually going into
so the last state is schedule this for retry.
Okay.
Basically, the retry scheduler get this event, and it check if not exceeding the maximum retry, it will set up timer for it.
And that's going to the expired event queue?
That is going into the sorted set. I didn't show up here is you set up timer in the sorted set. So the score actually is the time in future seconds that you are going to expire. So then this retry scheduler actually is looking up this sorted set and figure out who's going to expire in next second.
Okay.
So this is another kind of hidden work is I didn't show up here. Yeah.
How did you deal with the Redis master being a single point of failure?
That's really a very good one. Currently, we don't have a good solution here. Basically, is set up slave server. It got all this event. So in case Redis somehow smashed it down, we got a chance to set up this whole thing at the slave very quickly. That's the current solution. But I think the big challenge or next step for me is how do I do this thing in the Redis cluster?
Any other questions? All right, thanks a lot.
Thank you.